Yeah, so the last few years I've been working at the Mærsk McKinney Møller Center for Zero Carbon Shipping. It's a center with a very long name, but we thought there are some really interesting projects ongoing now, all to deal with or dealing with how to reduce greenhouse gas emissions from shipping and how to get to zero actually. And the idea was, can we do this by 2050? So I just give an overview of how the center works in the introduction and what kind of activities there are, and then focus on these items listed here in terms of the IMO strategy and the greenhouse gas emissions. Uh, then first of all, look at energy efficiency, because that's really actually something we can do right now, in terms of reducing our emissions and fuel consumption, of course. And then focus on the alternative fuels, because that's where, as we can see it, let's say the solution mostly will lie in terms of getting close to a zero emissions condition for shipping. So the center, as it's called now for by many where we work, it was started about 4 years ago by the Mærsk McKinney Møller Foundation. It was a Mærsk family essentially. They donated a lot of money with the idea to set up a nonprofit organization that would be science based in its kind of work activities and impartial, and with the idea to help the acceleration of the shipping industry to get to anywhere close to zero greenhouse gas emissions by 2050. So that's the background. Um, and if you look now over the years, these all the center activities you could say are listed or categorized under these four major programs. The first one, as you can see here, is reducing energy demand on the fleets. That's really anything to do with how to improve energy efficiency, how to help regulatory processes, and making, let's say, legislation, regulations that encourage energy efficiency uptake. How can you do this? What kind of frameworks can be developed for this? How can we share information in this area? The second one is the anything to do with the new fuel. So it's the energy system. How do we scale up, the green fuels? And this is really a major challenge. We'll come back to that one. And also look at what are the onboard vessel solutions that you would need, but also infrastructure development, production of the fuels, and so on. That's also all being considered here. And then there's this thing, about the ecosystem transition. This is something where we say, okay, how can we identify first movers in the industry, and maybe also in this realm of green corridors. And there are some actually green corridor developments also in Australia, from Western Australia to Japan, for example. There's another one that we've been looking at least, with, for example, between New South Wales, East Coast, and New Zealand. But there's 30 or so, 40 green corridor initiatives. I won't go any further detail in this area, but it's happening. So it's really initiatives to help accelerate this process of the fuel developments, the ships, etc. And then, the other one is more the whole looking into the policy developments. This is to say that could be in place, or can we help develop policies? It could be IMO, it could be regional, like in the European Union, to help also get this greenhouse gas emission reductions process working. Um, just a few more words. The center was started 4 years ago. Now there's about 130, closer to 140 employees, which are partially full-time employees and partially they're seconded by and the center has a number of partner organizations. And all with the secondees altogether, we have over 100, well over 100 specialists, and they cover the whole area basically. And this is super interesting because it's from the fuel supply side, people with bio, maybe fuel background, or it could be economists, it could be naval architects like us, all the way to say the cargo owner. So it's really the complete, as they say, the value chain that's represented here, and everyone had basically the same focus or aim, and that's really these partner organizations, and the 24 of them are the key partner organizations. We call them strategic partners. Yeah, they all say, yeah, we want to be part of this process of getting to zero somehow. We also have a number of we call knowledge partners, and actually the Royal Institution of Naval Architects is also one of them. You can see them listed on the right. So if you look at this from the other perspective, say, where are these organizations placed? It could be from the energy supply side, the technology side. For example, yeah, you can see some of the energy oil producers. They're also interested in, okay, what can we do with new fuels? Then there's, for example, MEN, Energy Solutions, but also Mitsubishi. We have, so anyway, let's see, you can see it's quite a variety of organizations that span that whole chain. So you have the ship owners, you have cargo owners, charterers, and then all the way to, let's say, the knowledge and the policy side. So with all this, we have quite a few projects. I think there are now about 40 or 50 projects running in parallel. But I'll just focus on a few. Starting with the IMO strategy, because I think this is one of the key drivers, you could say, for us industry to decarbonize. And yeah, you could say the first initial strategy was formulated back in 2018 at IMO, and at that time the agreement was to actually to aim for a 50% reduction in greenhouse gas emissions by 2050 compared with 2008. And also there were a number of short-term measures that were agreed at that meeting, and those short-term measures we still have today. So you can see here the progression from when it started, 2018, through where we are now and to the future. So we have the short-term measures, and here we have EEDI, and that's the Energy Efficiency Design Index that started already quite a long time ago, some 10 years ago. Then later on we got the EEXI as part of the measures. So that's basically the EEDI for existing ships. And the CII, which is the carbon intensity indicator. And we'll come back to that one because that one is more problematic, you could say, or challenging for some vessels than the EEXI. EEXI basically is just sort of power limitation that's being imposed on all vessels for some reason or somehow, but not to go further into much detail with that one. But then if you look at the midterm measures, those are now on the table at IMO, and those are really important because here we start looking into this market-based measures, and that's really basically greenhouse pricing mechanism, possibly in combination with what's called a GHG fuel standard, so setting some kind of limit on the fuel intensity in terms of its carbon emissions for the fuel that you're using on the ship. I will not go into further details to the midterm measures so much, but it's just there right now. So we are part of the discussions at MEPC. We're also looking at MSC when it comes to the safety of the fuels. But there's a lot of things happening, and so we have to really keep a good eye out on what's happening this coming year at the IMO, because they'll be really governing a lot of these issues when it comes to enabling, let's say, this transition, because these new fuels that we talk about will be not cheap. And so if you say there will be some kind of greenhouse pricing mechanism, hopefully that will cover the cost cap or part of the cost cap when it comes to the new green fuels that are produced or will be produced, hopefully using renewable energy and so on. That can be, let's say, at least taken partly by it's like a CO2 emission levy or whatever type of mechanism that will be agreed on. To really, because the thing is, time is pressing, and we have a lot of challenges. But then we had the 2023 strategy, which was really a major breakthrough, I would say, for IMO, because at that meeting, MEPC last summer, it was agreed to actually go much further than the 50% reduction target from 2018. And that's the first time I saw there was a standing ovation from the whole plenary session at that time at MEPC. So if we look at what was agreed, one thing is to, yes, so the agreement was to actually by 2050 or thereabouts go to achieve zero greenhouse gas emissions, together with a number of intermediate, you could say, steps and levels of ambition to look at, as stated here, the carbon intensity reduction. That actually was one of the short measures from 2018. So that has still been upheld. But then also looking into reducing, let's say, or encouraging uptake of 5%, maybe up to 10% of new fuels, zero GRAS, zero GHG type of fuels or technologies by 2030, and reduce the absolute emissions by 20 to 30% in 2030. And this is really, I think, a major ambitious target, because it will be challenging, but that's something that means we have to really start now with developing all the technologies and fuels to actually reach that point. And then you can see here by 2040 have some further reduction targets, 70 to 80%, which is also a lot. But of course, it's 2030 now. That's really a key. And you can see this is a summary from a nice DNV presentation of these decisions. So you can see here we already started in 2008, and then over the years we have to where we are now. Because if we were not, if we were just continue, you could say business as usual. That's the blue line upper one. It will go up because, as part of all the efforts we have now, trade will continue to increase. Which means more and more ships will, of course, enter into the world fleet. And then how do you do this while you're actually then reducing overall emissions? So that's one of the big challenges. Okay, so that's just the background. So starting with energy efficiency, you could say here, energy efficiency is something we can do now. It reduces overall emissions for all ships, because you save fuel, reduce emissions, but also that by doing this, it reduces the dependency or the demand for, let's say, the new fuels. So anything you can save there is, let's say, invested. And of course, it affects also the bottom line. The more efficient the ships are that we are running, the less the operating expenses will be. So the cost of transition will be lower. But then if we look at the and this is the energy demand curve. So if you look at we have 30,000 or so ships in the this is the above 5,000 gross tons. Those all the world fleet. If you look at its overall energy demand, it's about, say, 12, 13 exajoules. Exajoules may be hard to see what it means, but it's 10 to the 18th joule per year. And again, these curves sort of show if we just continue as we are now, we get this upper solid black line. And this is energy demand because of increase in world fleet, in spite of, let's say, any energy efficiency measures that have been taken now so far. So we really have to look at, can we bend the curve downwards and say, okay, how can we encourage the further uptake of efficiency increasing, enhancing measures, so we can actually get to these lower lines as indicated in this figure. But it's not easy, because if you say here, okay, we have, suppose if we want to reduce by, say, 10%, 1 exajoule, you can see here what that really would mean. And that would be, say, as you can see here, a third of all ships would have to have been fully optimized, which is a lot more than we have now. And you can see other things here like, and it means hull form optimization, propeller, energy saving devices, engines, etc., etc. A quarter of ships would have to then also actually invest in, yeah, you could say the more expensive technologies such as air lubrication, wind assisted propulsion, as we were just talking about. And there, you see here, it would be meaning a 400 times increase in what we have now in terms of adoption of these technologies. And this would have to all be done by 2030. So definitely a big challenge. And, if we did some analysis on, if you look at the different efficiency measures that are at our disposal, and it could be technical solutions, whole propeller design, engine systems, energy efficiency on board, new technologies, operational measures, of course, really important too. What you do with your hull cleaning, voyage planning, weather routing, all this kind of things you can do, the utilization of the vessels in the fleets, and so on. When you're on the picture on the right sort of paints, I think, a not so great picture. Say, well, which ship segments have invested or are doing this as a matter of standard procedure, you could say, design and operation wise? Then you could say the cruise ships, the passenger vessels, they have, it's more a matter of them. They do this now. It's almost all vessels. Container ships, they are sort of on their way, but not all of them do this. But it's very limited, as you can see here, as far as we could see, at least for the bulk and tanker sectors. And if you look at all these four sectors, they are really, and especially it's bulk carriers, the tankers, and the container ships. They already take care of the 80% or so of the total, emissions for the world fleet. So they are really important to have included. So the question is, then, how can one encourage the uptake of further energy efficiency for those kind of fleets? One thing is maybe you could say regulatory. We talked about EEXI, so that's the EEDI for existing ships. As I said, I'm not sure about its impact in terms of energy efficiency. But the other one here on the right, the CII, which is this carbon intensity indicator, that's would have likely a higher, it could have a higher impact on the uptake. So, and this has just started last year. The reporting is being done now for the first, let's say, year of operation, and let's see what comes out of it. If you look at how CII is calculated, there was a lot of work done on investigating all of the different shipping or ship segments, from in the cargo vessels and also passenger ship and ferry areas. Lines were drawn to say, okay, what is the um, let's say the carbon intensity for those vessels as a function of dead weight, and then the idea was to, and this carbon intensity is basically it's transport work with CO2 emissions per transport work. That's what's called carbon intensity. And the idea is that the required or allowed carbon intensity would be stricter and stricter, as the years go on. So you can see here the table in the middle. We're starting in 2020, which and then this every year is reduced by 1%. As of now, every year will be a 2% reduction until 2026. And after 2026, there's no agreed reduction yet. But so the idea is that every ship would have to then compute, and after 1 year of operation, look at this, what is the carbon intensity has been, and then you get a rating. Depending on the rating, or let's say how well you do, you get A, B, C, D, or E rating. And that's really indicating how efficient has the vessel been operated or designed and operated. So if you're in the D category, it means you're above the or allowed, or at least, or let's say intended target for that particular year. And then you have to come up with a plan to improve that efficiency and show that you are doing things to actually get back to a better rating, the C or the B or whatever it might be. Trouble is, it's not so easy It depends on the ship type and its operation, its trade very much. And one of the items is also that the CII, as you can see here in the right bottom, is expressed as the amount of CO2 emissions divided by capacity times distance. So this is sort of a proxy for transport work, but capacity meaning the dead weight. So whether the ship is fully loaded or partially loaded or in ballast condition, that doesn't matter. It would still get that kind of, let's say, the same rating. And this proxy is called the AER. It's like annual emissions ratio. Um, and so for some vessels, as said, it'll definitely, it could be a challenge. So you can see here just the principle of it again. So you have over the years, for a given ship type and dead weight, you get this kind of progressively more strict requirement for the CII. Um, when you are in this, you can be in the D rating for like 2 years or so, but then you have to come up with a plan anyway. If you have a ship in the E rating, which means immediately you have to come up with a corrective action plan, as it's called, which means you have really a limited time period to prove, let's say, that performance of the vessel from E to C or better than B. Now, if you look at the and this is causing, it will cause a lot of issues because you can see here as an example. This is based on data from end of last year, but just as an example for bulk carriers. We're looking at a lot of bulk carriers as a function of from small to the large size bulk carriers. Then you can see here the spread in the this AER, the CII, and you can see that some vessels are so the middle line, that's the mid C range. So if you are below it and between the green and the yellow one up there, you have a C rating. If you go below, a little bit below, then you have B rating, and way below you have the A rating. So you see quite a spread. Some ships are in the A rating, but you see also quite a few vessels in the D and in the E rating conditions. Especially for, let's say, the ships you can see here, say for the 50,000 or so dead weight, but also the larger vessels, the very large bulk carriers, 300,000 ton dead weight, you can see also on average are actually above the C category. So just to indicate, we have an interesting challenge here for ship owners and the charterers. And this is really the issue with CII because it's influenced by so many different things. It could be the vessel design process, how officially was it designed, how is it operated. It's the delays in ports that will affect this, factor, how the ship is maintained, and then there's commercial, decisions. All of these influence this. So that's, you could say, therefore, from a contractual perspective, also quite a challenge. Okay, just to be noted, but we hope at least that this will definitely focus everyone on the need to be as efficient as possible. Yeah, I won't go into much detail here, but just to indicate there's quite a long range of things that one can do to improve the energy efficiency. And these are just indicative, efficiency gains that could be expected, but anywhere, say, from a few percent to 10%, or maybe some even to higher than 10%, could be achieved. And by the way, we say here for wind assist up to 80%, 8%. This is wind assisted systems that have been tested and publicized, but there's also now you could say, instead of just wind assistance provision, you can have systems that maybe provide a significant amount of propulsion power. It could be 30 or 40% or 50% or whatever. But that's, let's say, coming up in the future. It's just, so these are numbers for, let's say, the typical cases where we're seeing the wind assistance system. But similarly, anyway, for other things like power generation, what can you do with frequency control drives or boiler optimization? So there's small things or big things one can do. There's a lot of things one can say. You can talk about hours about this one, but just to, I think is one really important thing is to be aware of ships, especially these kind of ships. So, for example, container ships, they have an operating profile which is yeah, you could say quite varied in terms of the drafts, the way the degrees of loading and speeds. Yet in the past, these ships were designed for one particular loading condition, which used to be fully loaded, high speed, like 24 knots, 25 knots. And during my McKinney days, you could see that this actually, we discovered, we're doing the wrong thing here, because those ships that we actually designing for one condition actually operate at such a variety of conditions. So it would be much better potentially to design the vessel and the hull form design, propeller design, engine design, rather than say, okay, I want to really minimize, or yeah, you could say the power requirements across the operating profile rather than just that for the one design point. So this has had a major impact, but you also could see it for tankers. Tankers or bulk carriers. They also can have a range of draft conditions, and you could see it, for example, in the effect on the bulbous bow. And this is just a retrofit example on a container ship. It was designed originally with the bulb on the left. Your typical old, good old-fashioned bulbous bow. But then we looked at what can be done to you can use for this CFD model testing to say what can you do to optimize the bulb for its operating profile, and then you can see you get a totally different, or at least rather different looking bulb, and just the bulb modification that gave overall, I think, an average fuel savings of about 10% or so. So anyway, we can do the same with propellers, energy saving devices, and of course anything inside the vessel too. And when it comes to the energy demand, and there's a lot of things one can do here too in terms of things like waste heat recovery, also for smaller systems on board, combinations, battery systems. So we can see now coming up um, for ships, maybe not for propulsion and for the big ships. We can, I think, forget that for the moment being, definitely, but maybe also for power generation. So you can let your auxiliary gensets just run on a constant level, and when you have a peak demand, you could maybe then have a battery system that could take up the peak, and so on and so on. So anyway, there's a lot of things one can do here. Lastly, it's really important, even more important now, than to have a very good information on how ships are performing. And so it means you have to do performance monitoring, very accurate, at least measurements of your fuel consumption. What are the conditions? Can you note when the ship, the hull gets fouled or the propeller gets fouled? Um, Engine maybe inefficiencies. They can all be detected, but you need to have a good system on board. Here, this could be another item for talking, about for hours. But it's a really important, and also as alluding to earlier, when we have a greenhouse gas pricing, a CO2 or whatever levy coming up, that means it will be even more important to have a very good information on what is the actual fuel consumption on the vessel. Okay, a few words about carbon capture, because this is also one that's been noted as one of the potentials for shipping to make an impact on its, reducing its greenhouse gas emissions. And carbon, definitely, in principle, it is possible to do this. And last year, with a number of the center partners, some really detailed case studies were evaluated, looking into carbon capture on a container vessel. You can see here 15,000 TEU, but also a smaller tanker, a VLCC, smaller bulk, and a big bulk carrier. And that's also looking at different fuels. It could be just a conventional fuel oil, LNG, or methanol. Um, And you can see here on the right the picture of the VLCC, and the VLCC turned out to be, if you want to do this, maybe the more suitable type of vessel, because the dead weight of the vessel wasn't much affected because you have additional weight for the equipment, space. Here you have space on the decks to put, let's say, your liquefied CO2, because you get a lot of CO2 out of when you try to capture everything that's coming out of the funnel. You can see here some pictures of how how the impact would be on the superstructure area, on the engine room, and so on. Now, for me at least, one of the big surprises was that the extra energy required, to do the capturing is significant. Of course, it depends on the CO2 capture plant, but what we have seen, and this is amino-based system from Mitsubishi here, but I think you get similar things for other systems. At least I've not seen the one that's, let's say, very efficient, but just to indicate here, to get about 80% capture rate of your CO2, you need another 40 or so percent extra energy to just run the equipment, basically. This is indicated here for a ship running on just low sulfur fuel oil on the left, LNG in the middle, and methanol on the right. With LNG, you get a better efficiency, because with LNG you already have the, let's say, the cryogenic cooling capacity, because the LNG, the fuel, has to be cooled to minus 160 degrees. And that already can be also of use when you have to liquefy the CO2 that you capture. So this is just to show the tons of CO2 emitted per year, per day for the vessel, the extra when you have the, let's say, extra auxiliary engine power that you need, or for whatever source on the ship, you then reduce by 80% or so, and this is what you then the final let's say, figure you can get in terms of captured CO2. And then we should also note that, of course, because you have that extra energy requirement, you also need extra fuel, obviously. And if that's conventional fuel, normal, let's say, fuel oil, then you need to also look at it's part of the impact on the total emissions. But even when it's, let's say, a green methanol or some green fuel, it will be significant. So, and also if you look at the cost, different cost estimates were made here, but overall, the conclusion was that it's in a significant cost. So you have maybe 30 around 40% at least of your new build cost would be just the CO2 capture plant. And then if you look at the cost figure on the right, that's the operational expenses for this, again VLCC. You see a significant additional cost because of the additional fuel, compared with, say, the case where we have no carbon capture. So leave it at this. There'll be more, definitely work. It is ongoing. More proposals or information coming into IMO on this from different countries, member states. And the other thing, of course, is that you must also look at the total in its totality, right? What do you do with the carbon captured that you have? Where do you bring on shore? What is going to be done with? How do you ensure that that carbon will be used either to just store it on the ground permanently, or can it be reused for producing, say, a methanol type of fuel? Anyway, so still to be followed up. Then finally, a few words about the fuels, the new fuels. I think the important thing is just to look at the types of fuels, because we, of course, often have the fossil fuels now. Biofuels have been coming up, and that means there's any kind of a biomass or a waste product, agricultural waste or whatever, that can be used to produce some kind of biofuel. But the other one, the big one, you could say, are the e-fuels, so electro fuels. And the idea here is that those fuels would have to be produced with renewable electricity. and water. If it's going to be an e-fuel with carbon, for example, methanol, then you also need to do carbon capture, and that could be at a point source, or it could be from atmospheric direct air capture, possibly, or from biomass. So there's different ways of making such e-fuels. And the other one is you have also e-fuel. There's only one that we know of, at least now, without carbon. Maybe okay, no, so it's like ammonia. Hydrogen also, yeah, it's what you basically need together with nitrogen that gives you ammonia. So anyway, that's the quick rundown on the e-fuels. And if you look at then what are the fuels of choice, there's a lot of different fuels we have see right now. Besides the conventional HFO or MGO, we see LNG, LPG, even ethane, methanol, etc. You can see the long list here. But if we then look at what do we see as the likely um, close to or zero GHG fuels for large ships, for deep sea shipping purposes, will be biomethane. So it's like not LNG, but it's like LNG, of course, but then with a bio source, or it could be e-LNG, like we just talked about, like let's see, the electrofuel process. But biomethane is more likely as we see it now. Same with methanol. It could be a biomethanol or it could be an e-methanol. Ammonia, e-ammonia, and biofuel. So those four, you could say that's what's going to be, let's say the selection that we can foresee for the future. Hydrogen is very important for, as a basis for these fuels, but hydrogen by itself, yeah, it can be used as a fuel for really small vessels, but there are a lot of issues with hydrogen if you really would want to put it on a large ship for deep sea ocean voyages. The temperature, it has to be minus 253 degrees, or you would have to pressurize it to a 700 bar, to liquefy it. It has to be liquefied. So there definitely a lot of practical issues with hydrogen, but maybe we'll see it still in the smaller vessels, small ferries, for example, short distances. We have not looked at yet at, for example, nuclear power. There's some work here and there going on to consider, again, to look at whether nuclear propulsion plants are feasible. Who knows? You could also say maybe nuclear power could be used at least to produce, the greener fuels. Just because it's a zero greenhouse gas electricity producing way. And there's bioethanol and e-diesel, which has a high cost. So anyway, so for now we can see those, let's say, the green ones here on the left bottom corner. And if we look at the uptake now of fuels, let's say these are ordered vessels, and if you look at the number of ships that have, and this is from September 2023, from DNV, they make actually these nice overviews that you can get into. But if you look at the from the, let's say, the ships on order, there's quite a large number of vessels that have been ordered with hydrogen. You can see LPG, methanol, battery powered, LNG. It's a big one. Well, if you then look at it from the gross tonnage perspective, you have the picture on the right, on the bottom right. And you can see here that about 50% then is conventional fuel, and the other 50% is more the non-conventional, the new fuels, including LNG. The batteries you hardly see because it's only really for small vessels. Again, batteries are not really suitable for propelling big ships over large distances. It's just to indicate that it is happening, and so definitely methanol. We see quite a few ships that have been ordered to run on methanol, and then that should be then the green methanol. Um, but also now we already see ships that are ammonia ready, because ammonia engines don't, are not available yet on the market scene, but they will be soon, next year or in the course of this year, later this year maybe. we see the first ammonia engines appear. So there's a lot of things happening. You can see here this map of locations where there's say blue and green hydrogen projects, ammonia projects. And it's really accelerating. And definitely, you see Australia, quite a few initiatives here too. I won't go into detail, but again, this makes it also hard to say which fuel is going to be the answer. We're definitely shifting from the single fuel that we had in the past, just the basic fossil fuel, to a multitude of different fuels. And it will be hard to say which ones will be preferred. It depends on the vessel types, the trays, production cost, etc., etc. At least here you can see the basic schemes in which those green fuels can be produced. And then say, okay, and at this center here, McKinney Møller Center, a lot of work has been done in terms of developing a simulation tool that really captures everything from, let's say, the fuel production pathways, feedstock availability, to shipyard capacity, ship forecasts, retrofitting forecasts, energy efficiency uptake, owner decision making, the influence of greenhouse gas pricing. So anyway, so there are a lot of different scenarios one can develop. But so this is one of the scenarios you can see here. And so this would be one of the scenarios that would lead to a zero greenhouse gas emission situation by 2050. And you can see here that we have LNG coming up now, but LNG by itself is not really a zero greenhouse gas fuel, as we should know, right? Of course, it maybe gives you a 20% or so at most reduction compared with normal fuel. But then if you go say, but if you have an LNG fuel ships, it can be then also burning biomethane, basically the same, but it's from a biomass background, and that could be seen as, let's say, a net zero type of, or close to net zero situation. And then we can also expect, for example, the blue ammonia. This means it still has a component in the production process from, let's say, conventional fuels in it, but it has a significant reduction in GHG emissions. And then you get the e-ammonia coming in, say, in mid 2030s, for example, here. And that's really, let's say, the green zero type GHG emission type fuel. We have biomethanol, the green one here. So anyway, but again, these scenarios depend on so many of the different situations that you're modeling. But at least we want to get an idea of how that behaves. A quick word about life cycle, because this is also really important when you start looking at the fuels. One thing is the emissions coming out of the funnel. That's we call the tank to wake part, and that's just a function of the type of fuel and the type of engines, engine load, etc. You get your CO2 emissions, plus maybe other components that have a greenhouse gas effect. But then you also should look at the well to tank part, because you could say, well, for example, if I um, burn hydrogen, in the hypothetical case, I have zero emissions. But then if you need a lot of energy to produce pure hydrogen. That would cause that image to completely change if you then look at it from the well to wake perspective. So therefore, and they're the same for all the fuels. If we look at the next example here, you can see this is the different categories: well to tank, tank to wake, and the well to wake emissions from, let's say, for LNG. And as I said, LNG definitely is not, let's say, zero greenhouse gas fuel, but this is what you would get. And then if you compare with, say, the e-methanol, so the green methanol, methanol has a tank to wake emissions, you could see here, close to 70, and this is CO2 equivalent per joule, gigajoule of energy, but it doesn't matter. But then the well to tank part is let's say um, reducing the impact, because you actually doing a lot of carbon capture. You have to do carbon capture to generate the e-methanol using renewable energy. So that's offsets, you could say, your tank to wake emissions. Therefore, the well to wake net effect is very limited. Same with the e-ammonia. You can see here it has close to zero emission, but then you still need some. You have still some very limited emissions in the well to tank part. And the blue ammonia has a little bit higher well to tank part, because simply the process involves carbon capture, let's say from fuel oil resources. So therefore, and this is another item at the IMO as to how do we deal with the well to tank versus tank to wake. Yeah, just an overview here of the different maturity levels. We're trying to make these maps, as to, if you look at the different fuels that are now coming up, what's their maturity from the feedstock availability, but also from, let's say, bunkering perspective, safety perspective, emissions, and so on. And no need to go through all the details, but you can see here the red ones. That means there's some major challenging, and this is for the ammonia especially. It's from the bunkering perspective, also the regulatory perspective, emissions. Of course, for example, you could have ammonia slip or N2O, which is part of when you start burning ammonia, an issue, possibly safety. So here's definitely some challenges. Another challenge is energy density. And this is really interesting, because if you look at the different fuels, HFO has you can say, a relatively high energy density. So it's from the volumetric viewpoint. So this is the vertical axis. The horizontal axis shows the amount of energy you get per kilogram of fuel. So we look at, this is what we have now in terms of the current fuels, and that includes also some of the, let's say, the conventional biofuels. And then look at the comparison with, to say, the ones that are, say, the strong contenders, right? The new fuels, so methanol and ammonia. Say they have a lot lower energy density, which means we're going to be equipping our vessel, to run on methanol or ammonia, for that matter. You need, either a lot larger storage for the same range, or you simply say, okay, you accept you have a reduced range for the vessel, right? And then, but you have to bunker more frequently. So this is really an interesting item. Methanol is the example that you don't need to make any, let's say, refrigeration or cryogenic requirements, which you have to do still for ammonia, but it has to go down to, you can liquefy it at -30, -33 degrees. So that's and that's doable. So there's a lot of ways you can also make the conversion, from, say, LNG to ammonia. That's possible. Now, the other one, the last one here to mention, is hydrogen. And you can see here the challenge with hydrogen, it says a very low volumetric energy density. Plus the other challenges I mentioned in terms of you need to have a really high pressure to liquefy it, or you have to get it down to -250 or so degrees, which is a big challenge. So therefore, we can see it probably in, let's say, small containment systems. Fluid flexibility is really important, and as we can see here, just to illustrate, you can use different ways, to say, convert from, let's say, a monofuel engine to one that could be running on, let's say, methanol or ammonia. It is in principle possible, but costly. But if you have a dual fuel setup, say with running on LNG, then the conversion will be definitely easier to run, because then you have already dual fuel engines that are basically running on the fuel as a gas with a pilot fuel. You can make them ammonia ready, and also you can run, say, biomethane. So there's a more, I could say, you could say, range of waiting with the final selection of your fuel. So I think that's another reason we see a lot more interest in LNG fueled vessels at the moment. So you can make those, and then for example, the containment systems could be, say, okay, now you design for LNG, but then you can also make extra arrangements to make them capable of, for example, storing ammonia instead of LNG. So anyway, so that's interesting to follow. There's one thing issue with methane as a fuel, and that's methane slip. And this applies to all LNG fueled engines, but also running, it doesn't matter whether it's just LNG or biomethane or e-methane or e-LNG. And just the picture on the bottom here shows the different types of emissions. On the left, you can see here, that's the emission, or let's say in terms of the methane slip. And it's very low for the high pressure diesel engines. That's the one, the high HP two-stroke. But then if you have a low pressure two-stroke engine running on an Otto cycle, it has significantly 10 times higher so methane slip. But then you can have abatement systems such as exhaust gas recirculation. You can improve the emissions with that. And the highest emissions for methane slip wise are from the low pressure four-stroke engines. So your medium speed engines running on gas, they have a quite significant emission profile. And then, of course, and the problem with methane is it has a high impact on greenhouse gas. It's with a global warming potential, which is 25 times higher than CO2. If you look at it over a 100-year time frame, it's even 80 or so times higher over a 20-year time frame. So you really want to reduce methane as much as possible. Okay, lastly, just because we're looking at ammonia, for example, hazards are a key issue because it's toxic. It can be also to humans for sure, but also to aquatic life. What happens in terms of if you have, let's say, a sudden leakage in your containment system, where explosions could occur. So it's corrosive. So a lot of these things will have to be assessed, and there's a process for this, doing hazards, so hazard identification studies, and they've been seen in a lot in the last few years for all kinds of applications. Here, a few examples: bulk carrier, RoPax vessel, where you go through all the potential hazards, you rank them in terms of low, moderate, high, and then you look at what are the ways to potentially mitigate those risks. Um, what are the causes of those hazards, and then you say, okay, what can we do to again reduce the potential that hazard occur, or if it occurs, what can you do to mitigate its consequence. And here again, you see here a long list of all the things that could happen. So it's just a matter of trying to understand the potential hazards and then address them. Here on the right away is a picture of the MEN ammonia engine that is close to where I am sitting in the MEN test center here in Copenhagen. And they've been doing hundreds of tests on different issues with the emissions, fuel, pilot fuel. How can you reduce the pilot fuel, because ammonia is not a really, you could say, a good fuel for burning inside an engine because it has low flammability. Anyway, so there's a lot of work going on here. What can you do with capturing the ammonia? Because you don't want to just vent ammonia in the atmosphere freely. So they've been doing a lot of work on ammonia capturing systems that could be also connected with the engine system. So there's a lot of issues to consider. I don't think there's any, let's say, showstoppers here, but it's certainly an area for that has to be further analyzed and considered. So yeah, and here's just an example of what you end up with. You get these kind of risk matrices in terms of the frequency of the hazards, the severity, and that frequency times severity is a risk, right? And you want to get out of the red region and reduce it towards yellow, the green regions. And then this has been done for a lot of different ship designs. So we had one here in the bottom. You can see it's a tanker It's called the No Gaps project. It's together with some of Scandinavian organizations. So anyway, so it's something of great focus, because it's one of the potential fuels, which really you could say it has a zero greenhouse gas profile when you start burning it. So therefore, regulations in this regard are really important. There's a whole set, from the IMO, but also ISO have developing standards, SICTO and bunkering standards. And just to complete, this is the IGF code. So that's the code for the IMO that's for use for gas as a fuel. And it's covering natural gas, say for LNG, but then also looking at methanol, ammonia, hydrogen. So with all this, hopefully we can have the regulatory framework in place, and look forward to a future. Here I would like to